The inertia tensor of the rigid body B about any point A expressed in the inertial frame B is given by this term on the right hand side, that is minus summation for all the particles from I equal to 1 to n mi Ri with respect to A expressed in the frame B cross Ri with respect to A expressed in the frame B cross. Here point A may be different from the center of mass C of the rigid body. It could also be a point which may move. The question is, how is the inertia tensor about the point A related to the inertia tensor about the center of mass C? For this, we'll break up the vector Ri with respect to A expressed in the frame B as Rc with respect to A expressed in the frame B plus Ri with respect to C expressed in the frame B. This is just simple vector addition. We can derive the cross matrices from the respective position vectors on the left hand side here, and they are given like this, and we substitute this in this expression for the inertia tensor about the point A. We get inertia tensor of the point of the body about the point A expressed in the frame B as equal to this expression here. Now let's expand this. When we expand it, we get these four terms. Now here you can see that when you collect the terms together, coming to the first term here, Rc with respect to A cross, it's not affected by this summation sign because there is no index I over here. So you can take this outside the bracket, outside the summation sign. So you have here minus summation mi, which amounts to the mass of the whole body, Rc with respect to A expressed in B cross Rc with respect to A expressed in B cross, plus this one again, it's taken out of the summation sign. You're left with mi into Ri with respect to C expressed in B cross. That's here. Plus here the order is slightly different because the order of multiplication of these matrices is different. It seems interchanged with respect to this term here. Plus the last term, which you can recognize, is the inertia tensor of the rigid body B about the center of mass expressed in the frame, this last term over here. So this expression, this equation, here we make use of the moments of all the particles on the rigid body about the center of mass expressed in any frame that's equal to the zero vector, and so the corresponding cross matrix is also going to be a zero matrix. Consequently, these two terms are going to be equal to the zero matrices. So we are left only with the first term here and the last term here. So we write this expression like this: Rb with respect to A expressed in the frame B is equal to this. Now if we substitute mi, summation mi for all the particles of the rigid body as equal to the mass of the rigid body given by mb, and the position vector C with respect to A expressed in the frame B in terms of its components x, y and z components, then we can construct the cross matrix from this vector, and that cross matrix is used here. So when you do the substitution, you get the inertia tensor of the body about the point A expressed in the frame B as equal to this matrix here, which is obtained from the components of this position vector RC with respect to A, and also we make use of the mass of the rigid body plus the inertia tensor of the body with respect about the center of mass expressed in the frame. So here you get a relationship between the moments of inertia. Corresponding elements will provide the relationships between the corresponding moments of inertia and the corresponding products of inertia. This is how the inertia tensor about the point A is related to the inertia tensor about the center of mass